So, we have been discussing the band structure of materials, and this is a simple two dimensional system which I discussed many times now. This is graphene and this is the band structure of graphene. So, let us as I showed in the previous view graph, this is a E versus kx qi picture which is the same as this one. So, this is on a scale which is much compressed, but you can still see this all the points. There are 1, 2, 3, 4, 5, 6 points at which the two bands touch, and they touch linearly with each other. As I said, the touching is like this. So, this is these are the points at which these k and k prime points. There are 6 k and k prime points, as you can easily see from here. See, there are 3 k points and 3 k prime points in this. There are 6 vertices. So, at each of those points the two bands touch and touch linearly. So, the spectrum here is basically E versus E goes as k. Okay. But remember, this is true only very close to this Fermi point. Okay. So, there are 6 Fermi points, although this is remember this is a two dimensional structure. So, you will only have Fermi points and you will have a Fermi line, but the line is broken up because there are only 6 places where the two bands touch at the Fermi surface, and so there are 6 Fermi points here, although it is a two dimensional system. So, this line that is drawn is the putative line. Had these two bands touched along these lines, that line would have been the Fermi level at half filling, but Fermi surface at half filling. Surface means a line here in two dimension. So, but that is not happening. What is happening is that there are gaps in between, and at only 6 points the two bands touch, and these are the points which are the Fermi points at half filling. So, usually the normal graphene has these 6 Fermi points. Now, the usually if you look at the band structure, one actually shows it in this way, because in 3 dimension, for example, you cannot do this. You have kx and ky and energy on the other axis. So, you only have 3 axes you can show visually, but in 3 dimension you would need a kz axis as well. So, that I mean usually one can do, what one can do is that take sections along certain kz and still show a 3 dimensional plot like this, but a better way is the conventional way is to show the plot as shown is in the lower graph. The these are the symmetry direction, as I said, the high symmetry directions, for example, gamma m, then gamma k, and then k to m. So, along these directions, remember that so gamma m, m k and gamma k, these are the directions along which one plots the bands, that the E versus k is plotted along these. And as you can see, at k point there is a linear spectrum very close to k point, but as you go away from this k point, as you go higher up, you can see that the linearity does not survive anymore. It becomes quadratic or different powers of k from linear in k. So, linear k spectrum survives only in this region pretty close to the k and k prime points, those 6 points. So, the Brillouin zone is shown here on the left hand side, along which direction the author is plotting is also shown. So, the author is plotting along these lines, dashed lines, gamma m, gamma m k and k gamma. So, for example, it starts from gamma, then comes to k. So, gamma to k, then k to m, then m to gamma. So, it completes a full circuit gamma k, k m, m gamma. And this is very usual way of showing the band structure, and it actually the high symmetry directions basically tell you what the bands look like, and almost all that you need to know about the band. Of course, if you would like, you have the information of the entire band structure at every point in the Brillouin zone. So, if necessary, one can also look at those, but usually the high symmetry directions are good enough to plot, to show the nature of states and the whether there is a gap, there is a metallicity, there is a semiconductor conducting behavior, or so on and so forth. So, graphene, for example, is like a semi metal. It has only 6 points where there are zero energy excitations available. At all other points the spectrum is gapped like a semiconductor, whereas at 6 points it is like a metal, but that too the density of states is very low at exactly the Fermi points, because it just touches that point, as I shown like a V. Now, let me go back to how does one calculate the band structure in such a situation. So, that is lattice, so called lattice with a basis. Okay. So, this I will go through quickly, because this is actually a very important thing, but this already, I mean, how to calculate a tight binding band structure I have already discussed, but the special case of where when there are more than one atoms in a unit cell is important, and because graphene has become so important these days, one such example I will just show, and then I will let you work out the band structure of graphene if you want to. So, remember the calculations that we did in which the matrix we formed was like this. Let me use black ink. Epsilon naught T 0 0, then 0, sorry, then this is minus T. So, this is also minus T, minus T, epsilon naught minus T 0. It goes on 0 minus T epsilon naught minus T 0 0, so on and so forth. Now, there is one thing that I mentioned, that if you have a periodic boundary condition, for example, you have to your first site, for example, in this chain the first and fifth sites are nearest neighbor now in a periodic boundary condition, because you have to fold this back here. So, that means this element, the last element here, will also be minus T if you are using periodic boundary condition. Similarly, the last element here will also be so 1 n and n 1 element will be minus T if you are using the periodic boundary condition. Otherwise, you do not have in an open boundary condition, these will all be, these are all zeros. So, this is the only difference between a periodic and a so this one this then u 1 u 2 and so on, u n equal to E u 1 u 2 u n. That is the difference between the two cases. These terms in the square bracket exist for periodic boundary condition, and they are set to 0. They are 0 basically in the open boundary condition, because in that case you do not have the last one nth one as a neighbor to the first one. Okay. So, this is how the matrix that we wrote down, but this is for a unit cell containing only one atom. Now, what happens if I have more than one atom in the unit cell? I will just show you briefly how to do this. The same thing can be done, same block theorem can be used for that case also. Okay. So, let me just start with a situation where, for example, I have two atoms denoted by circle and cross, then circle and cross, circle and cross, circle and cross, and so on. So, this is so these atoms are, let me call them A and B, AB, 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 and so on. I will use open boundary condition for the time being, but that is just a matter of convention. You can it depends on the system that you want to work in. So, this again what I do is that I will follow the same procedure that I did for the previous case. I will write down the LCAO wave function, which is a linear combination, as u m some phi m plus u prime m phi prime m. Okay. This is how I will do it. So, this what am I doing? What are these two phi m and phi m prime? So, phi m and phi m prime, phi prime m are the orbitals that I am using from the mth unit cell. So, what is a unit cell here? See, unit cell consists of these two atoms. This is one unit cell, this is another unit cell, this is one and this is one, and so on. And each of these two atoms A and B contribute one orbital each. These orbitals I call phi. So, from A I get phi m, and from B I get phi prime m. So, m denotes the location of, this is basically the unit cell location, mth unit cell, this is third, this is fourth, and so on. And phi prime are the two orbitals contributed by the two atoms A and B from each unit cell. So, this is again the same prescription that I did, but of course, the matrix will now become a bit more complicated. So, let me just carry on doing it. So, again I will do the same variational principle, and actually without even doing that calculation one can write down the structure of the matrix. Now, there are two kinds of so called hopping integrals, which earlier gave me minus t. One hopping happens between the two atoms A and B here, right, in the same orbital. The another hopping that happens is it happens between these A and B orbitals in the nearest neighbor unit cells. So, there are two kinds of hoppings that one has to take care of, and since I am only bothered about the nearest neighbor hopping, I will not bother about x hopping or o hopping, a hopping or b hopping, for example. So, there are only two kinds of hopping. I will call them t and t prime. So, t is within the unit cell. So, let me call them t1 and t2, because then there is no confusion with this prime. So, there are two kinds of hopping. So, let me write down these integrals. One integral is the epsilon naught which is phi m. So, let me not write it, sorry, phi m h phi m. Okay. So, this I called the the hopping I also take this to be same, but it is not necessary that I have to take it to be the same, but for convenience, because the matrix I want to let the I want the matrix to look simple. So, let me just take this to be the same as phi prime m h phi prime m. I could as well take this to be some epsilon naught prime, hardly matters. Okay. So, because I have graphene in mind actually, because in graphene the two sides are not different atoms, but they are the same atom in equivalent position. So, for them for in that case this is true, that both of them being carbon atom, you can phi this epsilon naught is the same for phi and phi prime. Okay. But as I said, I can as well choose them to be different, there is no problem in that. Okay. There are other quantities which is say minus T 1, which is equal to phi m h and T 2 is phi m h phi m prime m plus or minus 1. Okay. So, what does as in my previous picture I showed, I can show you what I am doing. So, this is remember this I now basically called T 1, the hopping between these two, and this hopping I called T 2, minus T 1 and minus T 2. So, a hopping between the atoms in the same unit cell is called, look at this, T 1 is the mth unit cell, the phi and phi prime on both sides of H, whereas T 2 is mth and m either on the right or on the left, m plus minus 1, these is between different unit cells, and that is that I called T 2. And as I said, there is no inter unit cell where both sides are either phi m or phi m prime, because I am not considering any hopping between B and B and A at different lattice different unit cells. Okay. Okay. So, let us then write the matrix straight away. So, how do I write first the basis? Look at the basis, the way to write the basis is exactly the same. So, E times u 1 prime. Remember, let me just show you what I did. So, these u m and u prime m, so these are my coefficients. So, I will write the basis in terms of these coefficients, and each m will give me 2 coefficients. Okay. So, that is what I am doing. So, u 2 prime, u 3 prime, and it goes on up to u n prime. for a finite system. So, this is my basis. Okay. So, what will be the matrix? I will find out the matrix. So, again the same basis will be written here, u1, u1, u prime 1, u2, u prime 2 and so on, un, u prime n. Okay. So, now I have to construct the matrix. One thing is very simple, that the diagonal elements, because of my choice the diagonal elements are all epsilon naught. Now, the next element is between what? Between u1 and u1 prime. So, that is between phi m and phi m prime, Hamiltonian matrix element, which I know is minus T1. Okay. For the first site there is nothing else, and so I will just continue doing this. For the second, the interesting thing is, so this is 0 0 0 0 goes on. I am using open boundary condition. So, I will not have to bother about the 1 nth 1 2 nth here coefficient, the matrix element. Okay. So, the next one is again epsilon 0, but now let us see what is the situation. So, this was my arrangement. So, this is T1 between the two, and between these two is the T2, minus T1 and minus T2. So, that one T1 for the first one I have already used. So, but for the u1 prime, which is for this B site, I have a T2 also, it is to the next side. So, on the right hand side I have a T2, on the left hand side I still have this T1. So, on the right hand side I now have T2. Now, one thing is actually very simple, because the Hamiltonian is a Hermitian matrix, you actually need to only find one side of this diagonal elements and one side of it. The other side can be easily constructed by the property of hermiticity. So, for a real system, that means a symmetric matrix. So, if I have T1 here minus T1 here as 1 2 element, then 2 1 element has to be minus T1 again. For example, here I have 2 3 element minus T2, that means 3 2 element has to be minus T2 again, and so on and so forth. So, the rest are all zeros. Then again, as I said, I will write epsilon 0 here. Now, 2 3 element is minus T2, then 3 2 element will also be minus T2, and on that side I will have T1 minus T1 and so on. Okay. So, this is the structure of this matrix. It looks a bit complicated, but it is actually not. So, if you look at this matrix, it has certain elements, certain things which repeat. So, let me show you what repeats. So, now let us see, this is 0. So, the fourth one will have epsilon naught here. On its left hand side I must have T1, because this one was T1. Remember 3 4 was T1. So, 4 3 must be T1, and this will be minus T2, and it goes on like this. Now, look at the structure of this matrix. This motif, these 4 elements repeat along the diagonals, and these, let me write in a different ink, these 4 are repeating along the off diagonals, and this will carry on. Remember, this one will come here. So, this is again a green one, there will be a red one here, there will be a green one here on both sides and so on. But this green one and this green one are slightly different. See, this green one and this green one are slightly different in the sense that one is the transpose of the other. So, this 2 by 2 matrix, if I write this as a 2 by 2 matrix and this other one as a another 2 by 2 matrix, they are just transpose of each other. So, that is all I have to remember. So, then the next next calculation that I can do is very straightforward. I can write this as a similar equation as I did for the one orbital one site per unit cell case, and I will just write it down. But now the elements that I used there, they were just H11, H12, these kind of elements, T, epsilon naught, T, minus T and so on. Now, those will be matrices. So, the matrices are which one? The ones that I encircled in red and the ones that I encircled in green. So, let me write down, then you will see how it works out. So, let me write a matrix, let me redefine and write a matrix as beta equal to this is just a notation, I am just using a notation, I am calling it beta is 0 0 minus T2 0. Remember this under, I am putting a line under to just to denote that it is a matrix. So, beta under with an underline means that it is a matrix, just to remind myself. Then beta transpose, this matrix is simply 0 minus T2 0 0. Okay. So, beta transpose is just this matrix. Okay. And I have the other matrix, which let me call it alpha, which is the matrix that I know, which is epsilon naught minus T1 epsilon naught. So, remember these so let me go back one page. So, remember this epsilon naught T1 minus T1 epsilon naught, this is the red 2 by 2 matrix, and the green 2 by 2 matrix on the upper right is 0 0 minus T2 0, which I called beta, and this lower T2 matrix, lower matrix is 0 minus T2 0 0, this green one, that means it is just the transpose of the upper right one. Okay. So, that is what I have done. So, remember these were my green matrices. One is the transpose of the other, and this is my red matrix, 2 by 2 matrix. Of course, I will also use the identity matrix, which is simply I equal to in 2 dimension 1 0 0 1, that also I will use. Okay. So, let me just now write down the equation, the same matrix equation. Now, I can write as okay. So, let me define one more quantity, which is C m, which is u m and u prime m. So, this is a 2 by 1 vector. So, I will write everything now in terms of these objects. Any underline means it is a vector. So, I for example is a 2 by 2 identity matrix. Okay. So, let me just write down the equation. E times, you can check for yourself, multiply and check for yourself, will be C1, C2, Cn equal to alpha, beta, then all zeros, but these zeros are also 2 by 2 matrices, remember they are 0 0 0 0, 4 zeros, and then beta transpose alpha, beta, then 0, these 2 by 2 0 0 0 0 matrices. This goes on, and then so then again here I have beta transpose alpha, beta, and then zeros, and so on. Times this vector C1 underscore underline C2 underline Cn underline. All these are, these 0 underline is a 2 by 2 0 matrix. Okay. Then again do the same thing, exactly the same. Then I write this matrix Cm equal to A e to the power I m theta as before. So, I can write this, so take any mth column of this, suppose I just an mth column. So, that mth column now reads like epsilon E C m underscore equal to C m minus 1 underscore beta transpose underscore plus C m plus 1 beta underscore plus alpha underline C m. Okay. So, that is the sorry, I should write it on the right hand side. So, these are matrices. So, I should write this beta transpose beta transpose C m minus 1 beta transpose and beta C m plus 1. Okay. So, that is the matrix equation that one has obtained. It is a 2 by 2 matrix equation which one has to basically solve, and the way to solve it, as I said, I will exactly do what I did. I will use the a solution which is consistent with Bloch's theorem. So, what I will do is that I will show it in the next class and find the spectrum for you and show you how such a simple generalization works beautifully to calculate the energy spectrum for systems with more than one atom per unit cell. Here of course, I have taken only 2, but that can again be generalized to a larger number of atoms in the unit cell.